everyone. I hope you have waited for the second part of real numbers. Yes, today I am here with the same thing, which is having a very interesting and easy part of real numbers, that is revisiting rational numbers and their decimal expansion. In our previous video, we have learned the irrationality of numbers and the proof for any number which is irrational. We have learned how to prove a irrationality of number. Yes, today we are continuing with the next concept which is given in your textbook, that is rational numbers and their decimal expansion. So in this video we are learning what is rational number and what is their decimal expansion, how will you convert a rational number or a fraction into decimal form, or how will you convert the same thing, decimal form of a number, into its fractional form. So let us go for solution for exercises with the concept explanation. This is Sharda Hegde. What do you mean by rational numbers? Yes, we have learned that in our previous class also. A number is of the form P by Q where Q is not equal to 0 is called a rational number. Yes, where P and Q are some integers. That means it may be 0 or positive integer or negative integer, but Q must not be 0. If it is 0, the number will become infinite. So Q must not be 0 and P and Q are integers. So this is called rational number. And also we have learned two different words regarding rational numbers, that is its decimal expansion is either terminating or non-terminating but repeating or recurring. We use those two words. Yes, once again I will repeat, either it is terminating or non-terminating but repeating. Yes, so in their decimal expansion we can observe two different cases. Let us take one or two examples to understand better what is fractional form of a rational number and what is their decimal expansion. Here I have taken two different examples. You are observing the first example. In which form it is? Yes, it is in fraction form. That means we are observing a numerator and a denominator, right? Yes, the denominator is 4 and the numerator is 97. It is a rational number because we represent it as P by Q where Q is not equal to 0 and also these two are integers, right? So it's a rational number. We can go for long division method. We can divide 97 by 4. Let us express this in its decimal expansion. You know the decimal value. Yes, we can go for long division method. We will get 4 2s are 8. So 2 will be in the quotient, and then 17, 4 4s are 16. Yes, so 4 will be in the quotient. We need to put a decimal point. You have learned these processes, right? And then the final answer is 24.25. We read it as 24.25. Yes, so what we did here, we converted this fractional form or rational number into its decimal form. Yes, can we convert this into fractional form? Yes, we can. How you will convert? Yes, we know 1, 2, 3. After 3 place values, we put a dot here. That means in the denominator of the fractional form, there will be 3 zeros. Yes. So our denominator will be 1000. Okay. And 375 will be in the numerator. Right. So now we expressed this decimal form into its fractional form. Yes, we have learned these two in our previous classes. In your textbook, they dealt with the expansion form, whether it is terminating or non-terminating but recurring. Without performing actual long division, we can say that whether it is terminating or non-terminating but recurring. We will learn that. We will learn those methods. Okay, and also there are three different theorems which involves these two concepts. Okay, the fractional form and the decimal form. We will learn that also. Before going to our actual theorem, we need to understand a small concept which helps to understand the theorem better. So here are the two examples which helps us to understand the theorem better. Okay, first I am taking 0.375. Can I express this in a fraction form? Yes, we know that. In our fraction form, I can write 375 divided by 1000. Yes, 3 digits after this decimal point. So now I am writing 3 zeros in the denominator, right? So 1000 can be written as, yes, 10 to the power 3. Yes, 10 to the power 3. As well as I can go for prime factorization. I hope you have heard this name. Yes, finding a prime factors for a given number is called prime factorization. For this example, I am going to give the prime factorization process in detail. But for this and all, for the coming example, we can directly write the prime factorization. Okay. So what is the prime factorization for both 375 and 1000? We will solve here. Okay. I will take first 375. So first we need to start with 2, a prime number, but the unit place is 5. So I can go for 5. 5 sevens are 35. 2 is left, 25. 5 fives are 25. Again I can go for 5. 5 ones are 5. 5 fives are 25. Now I can go for 5. 5 threes are and 3 ones are. So the prime factorization of 375 is 5 multiplied by 5 multiplied by 5 multiplied by 3. That means here it is repeated 3 times. 5 cube multiplied by 3. So prime factorization of 375 is 5 cube multiplied by 3. So in the numerator I can write 5 cube multiplied by 3. 3 means 3 to the power 1. Okay. Now I can go for prime factorization of 1000. Right. So what is the prime factorization of 1000? 1000. I can go for 2 here because end digit is 0. Right. So 2 5s are 10. 500. Then I can go for 2. 2 2s are 4. It is 10 now. 2 5s are 10. 0. I can go for 5 or 2 also. 5 5s are 25. 5 10s are 2 5s are 5 1s are. Okay. Now numbers are 2 and 5 and they are repeated. Right. So how can I write them? Directly I will write here. 2 is repeated 3 times. 1 2 3. That means 2 cube multiplied by 1 2 3. 5 is repeated 3 times again. Okay. 5 cube. So we represented these two numbers in their prime factors. Now I can say that any number, especially the denominator, that means in the form P by Q, I am talking about Q now. Q can be expressed as power of 2 and power of 5. Why 2 and 5 only? Because the denominator is in base 10 form. Yes, 1000 or in this case 4 zeros, right? 10,000. So how can I write that 1000 or 10,000 or 1 lakh? In the multiples of 2 or 5 only. Yes, because 2 and 5 are prime. I can't take 10 multiplied by 10 or multiplied by, because it's not a prime number, right? So only 2 to the power something or 5 to the power something I can write. We can conclude by taking one more problem, 0.0875, we can discuss here. So for 0.0875, how can I write a fractional form? Yes, in the denominator it is 10,000 because 1, 2, 3, 4 digits after decimal place, right? So 4 zeros and the number 875. Okay, so this is the fractional form. Now I need to find out the prime factorization of for both the numbers, right? So for 875 it is 5 cube multiplied by 7. Okay, so for 10,000, see one more zero, right? I can directly write 2 raised to 4 multiplied by 5 cube. Okay, by solving you'll come to know. Now I can say that the same thing 10,000 or the denominator q in the form p by q can be expressed as 2 to the power multiplied by 5 the power, right? In this example, so you have observed, because why 2 and 5 will come, you are having a base 10 number here, 10,000 or 1,000, 100 or 1 lakh. So you can express as, in general, 2 to the power n multiplied by 5 to the power m, 2 raised to n multiplied by 5 raised to m. So this is our conclusion. For any number, for any rational number which is in the form of p by q, for some integers p and q where q is not equal to 0, for that you can take the prime factorization for q, I am talking about denominator, will be in the form 2 raised to n multiplied by 5 raised to m, where m and n are non-negative integers. Please keep that in mind. N should be positive as well as m should be positive. Okay, this is one theorem and you are observing it is terminated here. Please observe, the number is terminated. You know the meaning terminated? That means the digits got end here, right? Here also there will be no other digits in the quotient. Okay, when you converted a fractional number into its decimal form. Okay, the first theorem is like this, and the second theorem is reverse of the first theorem. That means for any number p by q where q is not equal to 0, there will be 2 raised to n, 5 raised to m. Okay, where m and n are non-negative integers, then the expansion is terminating. Okay, this is second theorem, as well as the same thing continues, and the expansion may be non-repeating but recurring. Okay, we will take one example for all the three theorems and then we will solve our exercise problems. This is theorem 1.5 in your textbook that states that let x be a rational number whose decimal expansion terminates. Please observe that word. Then x can be expressed in the form of p by q, where p and q are co-prime. That means both are having only the common factor as 1. Okay, co-prime, and prime factorization of q, the denominator, is of the form 2 raised to n, 5 raised to m, where m and n are, the powers are non-negative integers. Yes, we considered example 0.375 and we expressed this number in the form of p by q. Yes, see, x, here x is 0.375. Okay, I am explaining this theorem with an example. Okay, so x 0.375 be a rational number whose decimal expansion, this is a decimal expansion, is terminates. Okay, so only 375, after 5 no digit will be there. Okay, so that means it is terminated, right? So terminates, then this x can be expressed in the form of p by q. How we have expressed? Yes, we expressed using denominator and numerator, right? that is 3 into 5 cube divided by 2 cube multiplied by 5 cube, right? So P by Q, in the form of P by Q we have expressed, where these two are co-prime numbers because 3, 5 or 2 is not having any common factor other than 1, and also the prime factorization of Q, this is Q of Q is of the form 2 raised to n, 5 raised to m, 2 raised to 3, 5 raised to 3. Powers may be different for any other example, but it must be 2 and 5, where m and n are non-negative integers. 3 and 3 we got here. It is a non-negative integer. I hope you have understood. So what it is saying, any terminated decimal expansion of a rational number can be expressed in the form of P by Q, where you can express Q as 2 raised to n, 5 raised to m. I hope you have understood concept better. This is theorem 1.6. Okay, the reverse of theorem 1.5. That means here you are observing, let x is equal to P by Q. That means we are taking a fraction first. Okay, it's be a rational number such that the prime factorization of Q is of the form 2 raised to n, 5 raised to m. That means first what we do, convert that fraction into the form of something by 2 raised to n, 5 raised to m. Okay, where n and m are non-negative integers, then x has a decimal expansion which terminates. Okay, so now then we can convert that into decimal expansion. Let me take 13 by 125. Yes, it's a different example. You are observing in the denominator, that means in the part Q, we are not having any base 10 number, 100 or 1000 or something, right? We are having 125. Now, in order to satisfy this theorem, the Q, that means the denominator must be in the form 2 raised to n, 5 raised to m. That means it is the multiplication of 2 and 5 should be there. How will you convert this? Yes, so we need to go for multiplying something else to this. Okay, first we will find the prime factorization, that is 13 for 13 because it's a prime number, and for 125 we can do like this. 5 ones are, yes, 5 twos are 10, 25, 5 fives are, 5 fives are 25, 5 ones are. That means 5 cube is the prime factorization for 125. So 5 cube I will write. Yes, I got this 5 raised to m, right? But I have not got 2 something, right? So I am going to multiply this by 2 cube. I should multiply the numerator by 2 cube because there should be no change in the value. Okay, so I have multiplied this 2 cube for the denominator as well as for the numerator. Now I can go for a number which will be in decimal form. By calculating this, we get 13 multiplied by 8 because 2 twos are 4, 4 twos are is 8. So we will get 104 by solving 13 multiplied by 2 cube, and this gives us, yes, 1000. Okay. So now the value, the decimal expansion I will write here. Please note down. It is 0.104. Our answer is, because 3 zeros, I need to put a decimal point after 3 digits. So my answer will become 0.104. That means x has a decimal expansion which terminates. We convert it into decimal form which is terminated. Yes, after 4 there will be no value. So it is terminated. This is a rational number. I hope you have understood this theorem. So our next and last theorem is 1.7, what they have given in your textbook. That is, let x is p by q be a rational number where p and q are co-prime, such that the prime factorization of q is not of the form 2 raised to n 5 raised to m. Okay, you are observing is not of the form 2 raised to n 5 raised to m, where n m are non-negative integers. Then x has a decimal expansion which is non-terminating. In your decimal expansion, how you will get? It will be non-terminating, but it is repeating. That means you will get a block of digits which will repeat. Okay, the block of digits will repeat in your quotient when you go for long division. Okay, let us consider one example. 1 divided by 7. If you go for long division, I hope you are observing here. Okay, the quotient, as a quotient you will get 0.142857 and again 142857 you will get. Okay, that means here your digits will never end, but you will observe a set of numbers, a block of numbers which will repeat, but it is a, yes, it is a rational number, right? So you can conclude from these theorems that any rational number can be either terminating or non-terminating but repeating. Yes, we can solve few problems using these theorems. Let us go for our exercise. Here I have taken exercise number 1.4. In that I just mentioned even the sub question number also. Please note that I have selected these three. We will discuss now whether the given problem is terminating or non-terminating but repeating. Okay, so these are the rational numbers. We need to now find out whether it is terminating or non-terminating but recurring without doing actual division. Okay, we know the theorems. Okay, so we need to go for denominator q, whether it can be expressed in the form of 2 raised to n multiplied by 5 raised to m. Okay, so let us go for the first one. Here we need to find out the prime factorization, but 13 is here because it's a prime number. The factors is only 1 and itself, so I can directly write 13. And if you go for 3125, I can go for prime factorization 3125. So end digit is 5. I need to divide it by 5. 5 6 are 30, then 12, 5 2s are 10, and then 25, 5 5s are 25. Now again 5 1s are, 5 2s are, 5 5s are, right? Again 5 2s are and 5s are, 5 1s are, 5 1s, sorry, 5 5s are 25, 5 1s are 5. That means here it is 5 is repeated 5 times. So how will you write? 5 to the power 5, right? That means here there is no value for, okay, 2. I can write 2 raised to 0, right? 2 raised to 0 is 1. I am multiplying this 5 raised to 5 by 1. There is no change in the value. So that I expressed the whole thing p by 5 raised to m and 2 raised to n. That means the expansion, decimal expansion is terminating because I expressed this as 5 raised to 5, 2 raised to 0, right? So the first problem is terminating. Without doing actual division, we can conclude the given problem is terminating. Okay, let us go for the second one. Second example they have given is 64 divided by 455. Now here also we can go for prime factorization. Okay, prime factorization of 64 we need to find out first. Okay, 3s are, 2 2s are, 2 16s are, 2 8s are, 2 4s are, 2 2s are, and 2 1s are. 2 is repeated 6 times. So in the numerator part I will write 2 raised to 6. Okay. Now 455 we need to find out 455. Okay. It is 5 here. I can go for 5. 5 9s are 45. 5 1s are. Now I can go for 7. Yes, 7 13s are. Okay. That is 91. 13 1s are 13. That means here I am getting 5 7 13. I should multiply, right? 5 7 13 gives you 5 multiplied by 7 multiplied by 13 gives you 455, right? So in my expansion I got the numbers other than 5 and 2. Okay, 5 is here, 5 raised to 1 is here, but other than 2 I got 7 and 13. So it is not in the form of 5 raised to m multiplied by 2 raised to n. That's why this is non-terminating but recurring. Okay, you can get recurring. That means after decimal point you will get a repeated set of numbers. Okay, so it is non-terminating but recurring decimal expansion of the given rational number. What about the third one? This means in your textbook it is sixth one. They have given only 2 raised to 3, 5 raised to 2. That means the whole thing is represented in the form of 2 raised to 3, 5 raised to 2. That means 2 raised to n, 5 raised to m. That's why the given rational number is in its decimal expansion, it is terminating, right? Like this, we can solve the problems. Please try the other problems in exercise 1.4. We will go for second or third main. The second main in the exercise 1.4 is you need to find out the decimal expansion for the problems which are given in first main. That means you need to go for long division. So I am not going to discuss that. Now we are taking the third main, which is saying that the following real numbers have decimal expansions. These are the numbers they have given. In each case, decide whether they are rational or not. Okay, we need to find out these numbers are rational or not. If they are rational, okay, if they are rational and of the form p by q, what can you decide about prime factors of q? Okay, what's your decision about prime factorization of q? Let us go for the first example. Here the number is 43.123456789, right? You are observing after decimal point the numbers are terminated. Okay, after 9 you are not observing any other digit. That means it is terminated. Okay, so decimal expansion is terminated. That is why it is called rational number. And one more thing they have asked, if it is rational, what about the prime factorization of q? We can conclude from the theorem 1.5, that is, if it is a rational number and then denominator will be in the form 2 raised to m, 5 raised to n, right? Where n and m are non-negative integers. So we can decide about q as it must be in the form 2 raised to m multiplied by 5 raised to n. Okay, so we saw the first example. What about the second one? After decimal point, you are observing 120, 1200, okay, 1200, 000, here 4 zeros, and it is continued, right? It is non-terminated. One thing I can conclude, and also it is not repeated also. If 120, I can find 120, 120, 120. Yes, it is non-terminated but recurring. But what is happening here? It is non-terminated as well as non-repeating, right? So it is an irrational number. Okay, the second one is irrational. So I will write R for rational, I for irrational. Okay, and the third one is 43.12345678 but they have given a sleeping line over here. That means you will observe this block of numbers frequently. Okay, one after the other. That means it is non-terminating but repeating. Okay, so it is also a rational number. So what about Q then? It will be in the form of, Q will be in the form of 2 raised to m multiplied by 5 raised to n. Okay, I hope you have understood. These are the rational numbers 1 and 3, and the middle one, question number 2 is, answer is irrational. Okay, we have solved the exercise 1.4. I hope you understood the concept and the problems very well. I hope you found the explanation as well as solution very useful. In our coming video, that means in real number part 3, you will be getting the explanation as well as solution on the fundamental theorem of arithmetic as well as Euclid's division lemma. So please be in touch with the channel Tricks for Maths for more such type of videos to get high score in your exam. And I will meet you in the next video with more information. Till then, take care. Bye-bye.